Hey folks, just wanted to give you a video of the following model activity. Um, so in this model activity, we have a solid block with mass 0.5 kilograms that is driving another solid block of unknown mass big M horizontally from left to right by means of an extensible cord that goes over a light and frictionless pulley. As depicted by the figure, the horizontal surface on which block big M is sliding has a tiny coefficient of kinetic friction, which we may practically neglect. So when you see this, that means we neglect friction completely. This problem is frictionless so far. The block little m is currently moving parallel to the vertical dashed line so that it was moving at 0.108 meters per second at x equals to 0.250 meters below the pulley, and it is moving at 0.358 meters per second now that it is at a coordinate x equals to 0.310 below the pulley. Neglect air resistance. So what's happening here is we have this pulley right here, and it's initially at a displacement of 0.250 meters below the pulley. And then this block ends up going down to 0.310 meters below the pulley. So it just goes down that difference between those two numbers. And the displacement happens isn't in the x direction as denoted by the problem, but rather the y. Part A is asking us to draw a complete free body diagram of the two blocks and to neglect air resistance. And then part B is asking us to calculate the mass big M of the block sliding on the horizontal counter in the setup. Again, neglect air resistance. Is big M in fact heavier than little m? So we're not going to get to part C just yet. Let's dive into part A, where we look at the free body diagram. So what I've done here is I've just reproduced the setup of this problem, where we have big block M. It's connected by a rope across a pulley to little block M. I'm sorry, to block little m. And when we draw free body diagrams, we always have to start with gravity, because gravity always points down, and it's an easy way for us to at least get some points when we have to, do this on an exam or anything like that, because every object has gravity act upon it. We're going to start with block big M, and that's the first thing that we're going to do. We're going to say gravity is acting with a force big mg on the object. Now, Newton's laws tell us that for every action, there's an equal and opposite reaction. So if gravity is pushing down on a surface, that means that a neutral force is pushing back up. So we can sort of create a recipe for how to draw free body diagrams. First, we start with gravity. If the object is on a surface, there must be a normal force. And then the third thing we have to take care of is a force of friction, but because this problem doesn't have friction, we can ignore it. After we've taken care of friction, we have to look at all the other forces that are acted upon this object. And after, counting 1, 2, gravity, and the normal force, the last force that we're left with is tension. So tension from the rope in this system is pulling this whole system to go right and down. So that means that tension is propelling block big M in this situation. Now we move on to block little m, and as always, gravity acts upon it, and that's immediately something we can draw. Gravity always acts on objects, it always points down. little m is not in contact with any surface, so we don't have to worry about friction. It's not sitting on any surface, so we don't have to worry about normal force. So that means that the only other force that's acting upon it is the tension pointing up on the object. Now, one thing about these types of pulley problems is that tension is always the same and equal in magnitude throughout the rope, which means that the tension that's pulling block big M is equal to in magnitude to the tension that's pulling on the block little m. And notice how the tension for block big M is propelling it to go to the right, whereas the tension for block little m is pushing it, I guess, to go up. And that's how these types of setups always work. So this concludes the free body diagram part of these two systems. Notice how I did not draw a free body diagram for the pulley. And now we proceed to part B, where we calculate mass big M of the block sliding on the horizontal counter. Now, we're going to start with a simple law, Newton's law, which is force is equal to mass times acceleration. And we're going to apply that to our system here. So in order to find the net force that's acting on block big M that's causing it to go left and right, we have to sum all the forces that are causing it to go left and right. In this case, the only force that's acting on the object in the left and right direction is tension. So the net force that's going to be equal acting on block big M is going to be its mass times acceleration. Note how I wrote big M to denote the object mass, and the acceleration of the object, which we don't know right now, is denoted by little a. This net force, which is equal to big MA, is also going to be equal to the tension of the rope, because the tension is the only source of this net force. And yeah, now the next step that we're going to do is we're going to sum the forces acting on block little m. Now, block little m has a gravity force that's pointing down and a tension that's pointing up, which means that the net force on block little m is going to equal to little ma, according to Newton's law, F equals to ma. And the sources of this ma are going to be m times gravity, which is the force of gravity pulling on the block, minus the tension. We have gotten to the point where we have two equations and a bunch of unknowns. So we don't know big M, that's what we're trying to solve for. We don't know the acceleration of the system. We don't know tension. We do know little m, we do know g, and then, again, we don't know tension. Although we have two equations, but more than two unknowns, it's still going to be a good idea for us to eliminate some variables here to see if we can come to a solution. So the thing that I'm going to pick to eliminate here is the tension big T, because it appears as a singular variable. It has no constants in front of it. So it seems like the easiest variable to get rid of in this system of equations. In order to do that, I'm going to subtract mass times gravity from both sides of the equation up here. And that gets us negative T is equal to little ma minus little mg. Now, multiplying everything out by -1, we get tension is equal to mg minus little ma. And what we can do now is take this tension and plug it into this equation up here. Now, what that transforms this equation into is big ma is equal to little mg minus little ma. And dividing both sides by a, which is the acceleration, we get big M is equal to little mg minus little ma over a. And we can take it one step further by factoring out m in the numerator. So now let's check what we know and what we don't. Little m is given to us in the problem. Gravity is always 9.8. We're good there. We just don't know acceleration. And this is where this part of the problem, where we're given a location and a velocity, is going to be used to find that acceleration. So there's also a kinematics aspect to this problem. Now, given two positions, two velocities, we need to find acceleration. And there's only one equation that we can do that with, and that's the forgotten equation, where v final squared is equal to v initial squared plus 2a times change in position. So v final is given to us in the problem, that's 0.358. V initial is 0.108. 2, acceleration's unknown, that's what we're solving for. And then the final position is 0.310 meters minus initial position, which is 0.250 meters. Subtracting 0.108 squared from both sides, we end up getting this expression, and then finally dividing both sides by 2 times 0.310 minus 0.250 gets us this expression down here. Plugging this into a calculator, we're going to get an acceleration of 0.971 meters per second squared. Now that we have A, we can plug it into this equation we derived for big M. For big M. Now, little m is given to us as 0.5. Gravity is 9.8 minus 0.5 again, our newly found acceleration, and then in the denominator, our acceleration is plugged in again. Big M is now 4.55 kilograms. Now, another part of the problem was asking us to do a comparison. So big M is greater than little m because big M is a much larger mass. Part B of the problem asks us to redraw the free body diagram and recalculate your answers in the event that the horizontal surface had an appreciable coefficient of kinetic friction of 0.22. So we go back to our free body diagram here. So we still draw our little ledge here. We still draw two blocks. We connect them with a rope across a pulley. But now we have friction. And as I've done before in part A of this problem, I'm going to focus on block big M first. And the first thing I'm going to do, just like I've done before, is draw a force of gravity acting on it. Drawing forces of gravity are the first step that you should do because every object ever has gravity act upon it. So it's a great way to get points on an exam just by drawing that there. Now, we're sitting on a surface, so that means there's going to be a normal force. That's our step 2. For every action, we have a reaction. So already two forces drawn. And because there's a friction force, present here, we're going to draw a force of friction, like so. Notice that force of friction is drawn at the bottom left of the object, and the force of friction is drawn to the left here because we are told in the problem that the object, the system, is moving to the right and down. And forces of friction are always opposite to the direction of motion here. So we identified gravity, normal force, friction, and now we're free to see what kind of other forces are acting on the object. And the other force that's acting on the object, that's not, part of our standard recipe, is going to be tension. The tension of the rope is still pulling big M to the right. So we're done with that free body diagram. Now let's focus on object little m. Now little m, like any object ever, has gravity act upon it. And because it's not touching a surface, friction's not something we have to worry about. because it's not sitting on a surface, we don't have to worry about normal force. So we're done at step 1, gravity. Now we are free to look at other forces that act upon this object. And in this case, it's the tension of the rope. Notice how, again, the tension is propelling object big M to the right, but it's pulling object little m up. Tension, because this is a pulley problem, is equal to in magnitude for both object big M and object little m. Let's see how friction ends up changing this problem. So, quick introduction. Force of friction is defined as force normal times the coefficient of friction. Now, normal force is also defined as gravity acting on the object. Actually, scratch that. Normal force is equal to and opposite to gravity. So the magnitude of normal force is going to be mass times gravity in this case. So, whatever's pushing the object into the ground, the normal force is the ground pushing back on the object. That's how you should think of it. And in our case, that normal force is going to be mass times gravity. Now, for object big M, the mass of the object is denoted by big M. We have gravity here, so this represents normal force. And then we have our coefficient of friction, which is 0.22. And that is going to be equal to our force of friction right here. Now, we still are going to do the same exact thing that we did in part B of this problem, where we use Newton's law that force is equal to mass times acceleration, and we're going to balance the forces initially on object big M and then on object little m in an effort to make a systems of equations where we could solve for the mass big M. Now, let's take a look at the new setup for object big M and try to analyze what kind of forces are causing it to go left and right. It looks like the net force on object big M is now going to be tension minus the force of friction. So force net is going to be equal to MA, which is going to be big MA for object big M, and that's going to equal to tension minus force of friction. Now, force of friction is force normal times mu, the coefficient of friction, which means that it's going to be equal to big M times gravity times that coefficient of kinetic friction. That means that the net force, big MA, is going to equal to T minus big mg times 0.22, which is that coefficient of friction. Now, let's look at the forces acting on object little m. We have gravity pulling it down. We have tension pulling it up. And that's it. There's no friction here. Therefore, the net force on object little ma is going to equal to little ma. And that net force is going to be equal to mass little mg, which is mass times gravity, minus the tension. We can rewrite this equation simply, strictly in terms of tension right here. So we still have two equations and two unknowns over here. And what I'm going to do again is just get rid of this tension variable. Again, the strategy here is just to, get rid of some variables so we don't have to solve for them. And since I rewrote the equation in terms of tension here, I'm just going to plug it back into this top expression right here. And that turns this expression into big M A, which is mg minus ma, and this is T, minus big mg 0.22, which is copied from up top. What we can do next is we can factor out little m out of this expression right here. And what we can do then is add big mg times 0.22 on both sides of this equation. On the left-hand side, we have all the big M terms, and on the right-hand side, we have all the little m terms. Since we're solving for big M, we're going to factor big M out to get this equation. Now we're going to divide both sides by this term and get an expression for M alone. So let's take a look at what we know and what we don't know. Little m is given to us in the problem. We know gravity. We do not know acceleration. We still don't know acceleration in the denominator as well. These are the same terms that are unknown. Gravity is known, and 0.22 is given to us. Now, we still need to solve for acceleration, but luckily, the point where we use kinematic equations to solve for acceleration doesn't change at all. Introducing friction changes nothing about the given, velocities and the positions that were given to us in part B of the problem. So what we do there is exactly the same thing we did in part B, where we use the forgotten equation to solve for acceleration, and we get the same acceleration, 0.971. And now that we have acceleration, we can plug it in to our expression for big M, which is 0.5, little m right here, 9.8, 0.97, 0.97 plugged in for A, 9.8 again, 0.22. And our answer for big M now is 1.41 kilograms. So in order for the system to move in the same way that it moved before in part B, but now with an added force of friction, the mass of big M has to be reduced. That's kind of like the physical intuition here. Introducing friction will change the system in some way. And the way the system changes is big M ends up being smaller. That's it for our recitation. Thank you.